All right, guys, today's lesson is on nonlinear regressions, okay? When you have data that does not make a nice straight line and you want to find a regression equation, your calculator will do that for you. All right, this lesson we're going to talk about exponential regression, and we're also going to talk about logarithmic regression. The shape of exponential growth and decay are these first two right here. The shape of logarithmic growth or decay are these two. Okay? Everybody got what they want off that slide? All right, well, data exhibiting rapid growth or decay tends to suggest a more exponential model. Data that will grow or decay rapidly at first and then slow down over time tends to suggest a logarithmic model calculated using the natural logarithmic regression, which on your calculator is going to be LNREG. Okay? Before we start today, we're going to do some little housekeeping things on our calculator. You need to go into y equals and clear out anything you have in there. And you need to turn your diagnostics on because we're going to talk about the correlation coefficient a little bit today. So if you would go on your home screen, second 0, the catalog, and then you either just scroll down to the D's or you can do the alpha key and then the D, if I could do it right. Oh, it was already an alpha. Thanks, that explains why it went off. Okay. Diagnostic on. Make sure you hit diagnostic on and it says done. Okay, can't tell you how many people turn diagnostic off and then ask me why their R isn't working. Does everybody say diagnostic on?
Do you have a question?
Yes.
Why is there even an option to turn it off? Like, why wouldn't you want to not have it?
Because if you're teaching, say, Algebra 1 in 8th grade and you're doing a linear regression and you don't really care to talk about what those are, it's just extra information that's on the screen for them to confuse them. That would be the only reason I can think of why you wouldn't want it on there. Does that make sense? Otherwise, yes, even honestly in 8th grade, I would have talked about the fact that that means it's a better equation if it's got a closer R value to 1. All right. Also, I would like you today to go to second window and make your screen look like mine, okay? Make it say ask and then auto. Now, this means when we go to the table in a little bit, it's going to ask us what value we want to go to rather than scrolling up and down a list of values, okay? I have no idea why, but some of the operating systems, it still gives you a list and it asks you what you want. It's really weird and I can't help you there, so I'll show you in a minute what we're talking about. All right, and finally, we're going to do a lot of Zoom 9 today. We're going to let the calculator pick an appropriate window. Okay, so when you can't see anything in your graph, you probably need to do a Zoom 9. And this is especially for people with the color calculator. Is everybody listening though? Whenever you're graphing something, thanks. Whenever you're graphing something, and you're like, oh, wait a minute, I didn't want it to do that, and it's taking forever, you just hit on, and then you can clear or go back and do whatever you want, okay? Anytime that your calculator seems to be just taking forever to go do something, just hit on, and then it'll let you hit clear or whatever. You know what I'm talking about when it's like graphing or it's frozen or something, okay? I had a lot of trouble with mine when I was doing this lesson on my color calculator. I'd go, oh shoot, I forgot to do this, or I forgot to do Zoom 9, and so it's graphing in a wrong window, and it takes forever for it to graph. So make sure you do the on thing. All right. We're going to start with a basic example here. The internet experienced rapid growth during the 1990s. The table below shows the number of users in millions for each year during this decade. Use exponential regression to model the data. So they're telling us what they want us to use. Okay, on the homework tonight, there will be somewhere they tell you which regression to use, and then there's somewhere you have to decide. And that's the hard part of this lesson. When they tell you, it's easy. Okay. We're going to use the model to predict the number in 1990. This is the trick, guys. You won't get the same answer I do unless you do X be the number of years after 1990. So we're going to put in 1, 2, 3, etc., all the way up to 10 here for list 1. And into list 2, we're going to put this data. All right, it takes me forever to do this on this calculator. It's stat, enter. If anyone has a whole bunch of garbage in there like I do, a good way to clear all your lists at once is stat plus, and then clear all lists. And then when you go back to stat, enter, they're all cleared out. Okay? Does anyone not have a list 1 or list 2? You want to put this in list 1 and list 2. We'll make it easier if we all do it the same. All right. I got that list quickly. This list is another story. I already screwed up, didn't I? Or is it rounding? Mine is messed up already. 1.142. 1.429. See, backspace doesn't work, and that's what always gets me when I'm doing this stupid calculator thing. All right, what am I on? 5.714? Ten. 21.4. Awesome.
Just go over to the number.
I know that, but the calculator and the keypad don't work the same. Oh, you have to hit enter twice, I think, is my trick here. I don't know. 21.429. The good news is I shouldn't have to wait for any of you, right? I should be the last one down here. 34.286. I don't know why they went out so many places on these either. 59.143. And then I hit backspace again. $70.314. All right, sorry. Now, what I want to do next is look at the graph. Is everybody listening? We're going to go second y equals. You need to hit enter twice so that the word on is darkened. If it is darkened around the word off, you have not yet turned your plot on. You need to scroll down one and make sure it is on the scatter plot, the first choice there. And then you need to scroll down so that it says list 1 and list 2. Then you're going to do your first zoom 9. And I don't know what I just did. All right. Now, honestly, if I had looked at this data, I would have suggested a logistic equation. Do you see how towards the end it appears to be slowing down its growth a little bit? But if you think about what this is internet growth in the 1990s, and we're going to use it to predict beyond that. And while internet growth may have slowed down slightly, do you think it leveled off anytime soon? No. So therefore, an exponential growth is a great equation, as we'll see here in a second. We're going to do the exponential regression. So here it says go stat, right arrow, down to the exponential regression, which is, I believe, 0. Okay? Now, I want you to store this. It's not an option here. You can't use the table if you don't store the equation. So if you have an 83 or an 84 that doesn't have this operating system, you will need to go L1, comma, L2, comma, Y1. Does everybody know how to do that? It's second 1 to get L1. Mine already says L1. Then comma, if you have an 83, because you have to just put it all in one line. And then L2, which is second 2, comma, and then all of us need to do Y1. So everybody go down to store regression if you have this operating system. We're going to store the equation in Y1. That is the VARS key, which is next to clear, the variables key. Are you on store regression? Okay, and you want to go to the VARS key, arrow to the right, and then hit enter twice. Everybody got Y1 in there? And then enter to calculate. I have to enter twice. All right, did anybody not get an equation and an R value and all that good stuff? Okay, let's write this down before we go look at the graph. I'm going to be lazy and just round a couple places here because I'm going to use the table to graph it and find the equation anyway. So I'm just going to write down 0.44 times 1.70 to the x, okay? A times b to the x. 0.44 times 1.70 to the x. I'm going to use all the decimal places to make my calculation because I have stored the equation. So if I go right now to my graph, here's what the equation looks like, graphed through those points. It does very well until the end, and then it kind of just goes between the last two dots. All right? If you go second graph, you should now be able to type in a value. Even if you have a table there, it'll let you type in a value. What is 2008 from 1990, guys? 18 years later, right? From 1990 to 2008 is 18 years later. Everybody okay? So we're going to just type 18, enter. And it's going to give us that value. Did everybody's give them the value of 5,900-ish? Okay, even if you had a table of stuff? All right, so on this blank down here, we're going to write 5985.7, and that's millions of users. So it would really be better to say roughly 6 billion, but I'm just going to go with that for right now. Everybody okay? Did some of you get a whole list of values there still? Yeah. I don't know why some do that and some don't. Because I looked and I couldn't figure out what was different. All right, I have to go back and redo. I didn't write down the R value, so I'm going to go back to the home screen and just hit enter again. My R was 0.991. So it was a good fit, okay? I want to do something really quick, and I don't want you guys to do this, but I want to show you what would have happened if we'd done the logistic graph. Do you remember what a logistic graph does? It's the one that flattens out. It takes a really long time to calculate this one, unfortunately, but I just want to show you. that while it looks like a really good fit here, okay, does that look great? When you go to the table and you put in 18 years later, you only get 91 million internet users. Is that a little bit of a difference from our prediction with exponential growth? Okay, so it's a very different prediction depending which equation you use. And I could show you also quickly that this is what the shape of that graph is going to do if I went out further here and further here. Do you think that internet growth has done this? I don't think it's flattened out quite like that, right? All right. We're going to go on to this example. Number 2 says the table shows average U.S. life expectancies according to birth year. We're going to use a logarithmic regression. That is the natural log regression. And what are we supposed to put in for our list 1? Anybody? Years since 1900, so this is going to be 50, 60, 70. Be careful. It goes 80, 90, 95, 100, and 105 out here. All right, so type those in as quickly as you can. If you want to go up onto the title and hit clear enter to get rid of your data, but do not hit delete. Is it 95, 100, and 105, guys?
Yes.
Unless you're me, in which case you just mess it up every time. Did I just pause that? Did I just do that now? It has?
I don't think it's paused. I think it's still going. It's still going. It's going. The time.
Why does it say restart then?
It's still going. It's still going.
Okay, I'm freaking out. 70.8. What's after 75.4? Somebody help me here.
75.8. And 77.0.
One more?
77.8.
Go. All right. Your list 1 and list 2 should still be in your stat plot. You want to go to y equals and clear out that equation. And then you can do a new zoom 9 to set the window, and this is what we get. Honestly, I would have looked at this as probably linear. If I had just graphed and looked at this, I would have said that looks pretty linear. But if we think for a minute, is the average life expectancy of people going to continue to go up in a perfectly straight line? It's going to slow down, right? I think we're going to probably reach some maximum life expectancy, and that's what a linear regression is going to do. All right, so stat, right arrow, down to LNREG, which is number 9. Okay, list 1, list 2, and store it in Y1. Is there anybody who has an older calculator who's not getting this with the commas? I can come help you. Everybody okay? All right, so write down all that information quick.
What do you want us to go to?
Just a couple places is fine because we're just going to use the table anyway. Did everybody get the same thing I did? All right, and then you want to look at the graph. Does this seem a little bit better than a straight up line? See how it's kind of flattening out just a little bit? And then if you go to the table, it says predict when, what was the question again, guys? 2020, which would be how many years after 1900? 120 years. So type 120, enter, and life expectancy of somebody born in 2020, they're saying is 15 or 79.2 roughly. Did anybody else get 79.2?
Yes.
Okay. Is your equation the same as mine? Or did you type a value in wrong? Life expectancy, guys, is kind of an average life expectancy thing. Obviously, you know, that includes people who die very young, and for the life expectancy is not, I mean, most of you who've made it to this age, you know, your life expectancy is probably greater than 79. But it's an average life expectancy across the world, so it's influenced by the fact that there are some third world nations where many infants die young. All right, guys, we're going to take this picture. I'm going to take this picture and slap it on here. Did you all write down some kind of a graph? Okay. Anybody have a question on this one? I want to get to the ones about where you have to test which one works the best. All right, are we ready? This is the top, or this is 24B. I'm going to jump around a little bit here, so follow the slides as to which worksheet I'm on. Exponential and logarithmic growth is unrestricted, increasing at an ever-increasing rate with no upper bound. In many growth situations, however, the amount of growth is limited by factors that sustain the population, such as space, food, and water. Such factors cause growth that was initially exponential to slow down and level out, approaching a horizontal asymptote. This is logistic growth. We did question about bears and rabbits last week, I think, maybe. Does that sound right? Okay. Logistic growth are bounded by two horizontal asymptotes. On the left, they approach 0, but on the right, they approach C, which is called the carrying capacity, okay, of this function. They want us to do one with a logistic model real fast. Go ahead and type this in list 1 and list 2. I forgot about this example. I want to get onto the testing as quickly as I can. Does it start with 0 or 4, guys?
0.
It's right there. Yeah, yeah. Yep. Clear out anything you have in Y1. Look at your data, see if you think, do a zoom 9, see if you think this is turning out okay. Okay, does it seem to be flattening out? Okay, go ahead and do stat right arrow. The logistic is down further. It's choice B. And I do want you to go ahead and store it in Y1 so we can look at how well it hits all those points, because a logistic equation does not calculate an R value. And it also takes, it says logistic, Logistic. Find it? Okay, and it does take a little while to calculate. It has 3 values that it has found for us. And the equation is C over, so C is 8499 roughly, over 1 plus A, which is 64.7, times E to the negative 0.39 X. All right, you will not get an R value within a logistic equation. And it looks something like this. We can go ahead and look on the calculator after it's graphed, and it is hitting all those dots very nicely. And this question didn't ask us to predict. It says a specific value. It says predict what it's going to approach. What do you think, guys? Yeah. If you went out, if you, for example, went to the table and you said, I want to go out 100 months or 200 months or whatever, it's getting really close to 8,500. It's actually would be limited at 8,499 according to our regression equation. But yeah, I did put down 8,500 fish, seemed about the max. Everybody okay? All right. Well, this is on 25A. Well, you can use a calculator to find a linear, quadratic, power exponential, logarithmic, or logistic regression equation. Your calculator will do all of those, okay? For a set of data, it is up to you to determine which model fits the data the best. You can either look at the graph or you can examine the correlation coefficient. I have little green arrows here pointing to where they put the correlations for all of these. It's pretty obvious that this data was not linear, not quadratic. Power regression wasn't bad, but the data seemed to be going up faster. Exponential regression was a very nice fit. That's why the R was 0.99. Everybody see that there? Logarithmic was not working. Logistic is really good. It's hitting all the dots. But you have to decide. Remember, logistic is going to, at some point, flatten out and approach a max. Over the domain displayed, the exponential and logistic regression models appear to be most accurate fit, while the exponential model having the strongest correlation coefficient. So it would totally depend what we were talking about, whether we picked exponential or logistic. We'd have to think about what the data was telling us. Is it something that's going to grow without bound, or is it something that's going to approach a limit? Yes?
How come, like, intuitively we think that R would equal 1 for the logistic?
We're going to talk about how the calculator finds R value in a second, okay? We're going to go to worksheet 25B next, guys. And by the way, it does suggest here that some models are better for predicting something short term, while a different model might be used to predict something longer out. All right, on 25B, the correlation coefficient is actually calculated on your calculator from a linear regression, okay? How do graphing calculators provide correlation coefficients for non-linear regressions? The answer is that the calculators have linearized the data, okay, transferring it so it appears to cluster about a line. The process of linearizing data has you taking, for example, an exponential equation. You would take the log to make it linear. So here's a set of data that looks very exponential. And over here, they've taken, right here, does everybody see this is x versus the natural log of y? So they took the log of all these and made them this, and when they plotted them, it turned out very linear. We are not going to true linearization, we're just going to do testing to decide which model is the best. All right, so hang with me here a second and it'll make more sense. Data can be modeled, et cetera, here. We're going to use these tests right here. Everybody has this on their paper, right? To see which of these turns out the most linear, and then we're going to use that regression equation. All right. So basically, to answer your question, Brennan, that logistic equation is so complicated that your calculator can't just undo it easily and make a line out of the data. That's a dumbed down answer for why it doesn't have a correlation coefficient. It's the best answer I have because I'm kind of dumbed down myself. All right, can you guys write these down? This is going to be really important. So next to those, when we do an exponential regression, when we test for an exponential function, we want to graph x against the natural log of y. So in list 4, we're going to find the natural log of the y values, which we stored in list 2. And then we are going to plot list 1 against list 4 because that's where x and the natural log of y will be. When we do a logarithmic function, we're going to, into list 3, put the natural log of list 1. And we're going to plot the natural log of x, which will now be in list 3, against y, which is going to be in list 2. And if we decide a power function looks like the best fit, the test for that is ln of x, ln of y, which will be in list 3 and list 4. We want to see which one of these shows up the most linear. I know. I'm going to show you in a second. Just write this down. I'm going to run through it, demonstrating on my calculator, and then I want us to do one. Everybody got that written down? Right down here? No. List 3 is going to be the natural log of list 1. And list 4 is going to be the natural log of list 2. And then we're going to plot L3 against L4. Nope, two separate things. Okay, I need everybody focused here. This is a set of data that's at the top of 26A. I don't want you to try to do this, okay? I want you to just watch. I have put this data into my calculator, and this is not going to show up for Sierra or whoever's watching the video, but I'm going to fly through these really fast. If I can get the glare off the calculator. All right, can you see it if I put it right there, guys? Okay, so I've put in the data from this list on your paper. Now, what we're going to do is we're going to go to list 3 and we're going to go up onto the title when we've done this, and we want to test these, and we want to take the natural log of the x's. Where are the x's? So we're going to do ln of list 1 and hit enter, and it calculates the log of all those for us. Then I want to do the natural log of the y's. Where are the y values? List 2. So I'm going to go up onto the title of list 4 and do ln of list 2, enter. All right. Now, my stat plot is set up to, I want it to graph, first of all, list 1 and list 2, so you can see those. All right, there's the data. Now, this is the original data. Everybody understand what I've plotted? This is the x's and the y's. We want to find a test that makes a nice line. What's the first test that you have written down there? It says to plot L1 and L4. Okay. Is everybody with me? Okay, so I'm going to my stat plot and I'm going to turn on L1 and L4 right here, and then I'm going to do another zoom 9. Now, kind of linear? What do you think? Kind of, but not perfectly? All right, what's the second test it says to do? L3 and L2. Okay, so that's natural log of x versus plain old y, right? All right, so when I do a zoom 9 here, this is what I get. Not even close to linear, right? But a power regression is ln of x, ln of y, is that right? So list 3, list 4. Is everybody looking for this miraculous thing that's going to happen here? Can you see those? Almost perfectly linear when we take the natural log of both sides. That means a power regression is our best fit. So if I were doing this question right now, I would go back and turn on list 1 and list 2. And then I would go and I would calculate the power regression. .999999. Okay? I didn't do a zoom 9 again. All right, and there it's gonna eventually graph that regression. See how slow that goes on the color? Okay? All right, so I want us to go back and I want us to try this. Okay, again, the idea is to graph the linearized data. If this test shows the points are linear, then it's a good model to use. We're going to go back to worksheet 25A and do a guided practice 4. Can you find this one? Start typing, guys, because it's a long list. What time are we out of here? Okay, we should.
Doing both of them? Oh, wait.
Yeah, you're supposed to put it all in. What's the last one? 16 is the last one?
Yes.
Thank you. Yep. All right, I have all of mine in. I am going to make sure I have nothing in my y equals. And I want a quick look at list 1 and list 2 because normally I would look and see if there's some thing that looks best right away. Okay? We're going to do all the tests on these because I want us to practice. So we're going to go stat enter. Everybody paying attention? Up onto the title of list 3, and we're going to do what there? LN, your LN button over on the left side there, and then list 1, which is second and a 1, and hit enter. And over to list 4, and do LN of list 2, and hit enter. All right. If you have a
You got 21 in there for the first one's 211.
Thank you. Anybody else see anything I did badly right away?
Yeah, I'm getting an error for when I type ln in list 2.
Why are you typing?
For the 0.
Do you have a 0? You can't take natural log of 0. Is that better? Yep. Okay. Guys, I want to get through these tests and we don't have a lot of time. So the first test we're going to try here is the exponential regression, which is the test is x ln of y. Where are those stored on your calculator right now? X is in list 1, and the natural log of y values is in list 4. So I want you to go to your stat plot, second y equals, and this time you need to scroll down here until it list 1 and list 4. Did you get yours to work?
Yeah, I did.
Okay. And then do a zoom 9. List 1, list 4, zoom 9. Not linear, right? Everybody get a graph that was not linear? Okay. Next test is logarithmic, or the ln regression, and the test for that one is ln of x, where's that? L3, and plain old y, which is L2. We want the best one. What is it supposed to be? L3, L2.
That's a really good representation.
L3, L2. That one's not too bad. Might be our best bet. And the next one is ln of x, ln of y, which is what? List 3, list 4. And what is that the test for, Brennan? This is the last one I got. Does everybody's look like that for the last one? Okay, so the best one was the second one, which was logarithmic. Okay, so let's go back to the question here and actually calculate the logarithmic regression. So you're gonna, if you want to see it, you're gonna have to turn back on list 1 and list 2. Yeah, it's the ln reg. Then we're going to go stat right arrow. Logarithmic is ln regression, which is 9. Sorry, it's 9, not logistic, logarithmic. There's no test for logistic. And we're going to, I'm going to store it anyway. And I'm going to write down what I get real quick. $263.5 plus 122.9 ln of x. All right, and it's 0.97 is the R value, so not perfect. If we look at the graph, what do you think though, guys? Is that pretty good? You have to turn back on L1 and L2 and do a zoom 9. Go second y equals. Make sure it says L1 and L2. Yes. Okay, 1 second. I'll come look. All right. Finally, we're supposed to predict the 18th month, guys. So we're going to go second graph. and type in an 18, and our prediction is there will be 619 domain names needed for the 18th month, or sold in the 18th month, or whatever. Caroline, could you stop the recording for me? Yeah.